So this video is going to be different from what I usually do. It's kind of a topology-ish paper, but topology isn't something I know a ton about. I know a little bit about it. I know enough to get like the basic idea of the main approach to the paper, but there's a part of it that I'm not like 100% certain on, so I'll say that, and I won't go over it because I don't understand it completely. But the main idea and the main approach I think is cool, and I wanted to show it. I would give resources on topology. I'm currently learning it, and all the like books and stuff I've seen are complete. Like they're all equally as bad. So any resource you find would probably be just as good as the one I'm using. But I think this would be a cool paper to cover, so I'm covering it right now. So topological spaces, specifically they're using cellular transformers. And kind of the idea with this cellular transformer is we're going to have our cellular complex, and we're going to feed this through a transformer somehow. So I'm not really going to go too in detail about the transformer either, so if you don't really know what a transformer is, I would suggest looking at something like the annotated transformer, but there's a lot of resources online for the transformer. But let's start off with like cellular spaces. So like let's say I have this manifold here, so some arbitrary manifold here we'll call fancy X or chi, and basically this is some arbitrary manifold. You can think of this as like R, so this would be like R2 bounded, and what we can do is we can break this up into disjoint cells. So we can take like this part here and we can break it into like a cell like that, or to make it look a little bit better, something like that. And we can break this all into cells, where cells are some arbitrary kind of partitioning of this space. So partition it like this until you cover your entire space, and you have these disjoint parts of your subspace, which each are a cell, and they can be combined together to create your entire manifold. So each cell is composed of multiple components, obviously. And we'll start with the two-dimensional case. So in a two-dimensional case, you have vertices, you have edges, so just draw the edges in between. And then you also have faces. So this would be a face right here. So that's what you have. And then in higher dimensional spaces or manifolds, you would break this up into higher dimensional parts. Now, this part here is homomorphic to a real space. So since this is R2, it's a 2-cell. This is homomorphic to R2 here. And all that means is it's this map that preserves structure, but isn't necessarily like a bijective map. A bijective map would be an isomorphism, but it's basically like you can take this space here, this R2 space, and you can kind of shrink it down into this cell here. And each part from here can be mapped to the cell using some map that you can define. And it can also be mapped back. And it preserves structures, so things like distances, perhaps. That may be one thing. Or like the holes in your space. So that's basically what we have. Now, this is kind of abstract, and there's like no data sets with this abstract manifold that is cut into cells. If there was, it would be cool. But let's go to what we kind of have already. So like what we kind of have is we have graphs. So some graph with vertices and edges, and the edges are connected in some way. So something like this. Here is a fantastic graph. So this is what we all know and love. Now, what we can do is, let's say we have, a graph that looks like this. We can do something called lifting. So this right here is composed of a bunch of 1 cells, which are just edges. And we can lift this by saying, I'm actually going to draw it like that. There. So we can lift this to another dimension, so one dimension higher, by making this a 2-cell here, by making this a face. And we define a face as something that is enclosed, so something that creates a cycle for these at these edges. So this is how we can take current graph problems, and kind of make them into this cellular problem. And the reason you would want to do that is current graph problems have a lot of things like over-smoothing, where if we do enough message passing, the every node basically looks the same because every node is kind of collecting information from every other node. So over-smoothing is a problem. There's a bunch of other problems as well. And lifting it to another dimension, or one dimension higher, where you're using faces, vertices, and edges, as opposed to just edges, can help with some of these problems. There was a paper, it was like simplical neural networks, and I was talking about how if you use 2 simplices, then it actually removes this over-smoothing problem. Now, what do you do with these? You can pass kind of along the face, and I'll show later how that's done, but this basically defines a relationship. So with edges, you have a relationship between vertices, but here we don't just have if we just looked at this graph and we didn't have this face, we can say, oh, this vertex has a relationship with this vertex. This one has a relationship with this one. This one has a relationship with this one. But it's difficult to kind of say all of these are related to each other. But if you have a face here, you basically say that they're related. And this will be one of the cells. So now in classic machine learning, normally what you do is you will take this and you just throw it through a transformer, like you always do. So that's what we're going to do. We're taking this and we're going to throw it through a transformer. So yeah, cell complexes. Now what you can do is you can define a cochain space, and a cochain space is always, I hate how it's defined in topology books, but it's because you need this abstraction to define it in the most abstract way as possible. But for what we're going to do is we're going to define this as a map from a cell to a vector. So they have a good diagram down here. Let me just show that instead of drawing it out. So if we have a cell here, we'll let this be our cell. So it's just, it's actually exactly, it's exactly what I drew over here, just flipped, or just mirrored. So that's kind of funny. But yeah, you have these vertices here. So these will be our 0 cells. You have your edges here. Those will be our 1 cells. And then you have your 1 face here, which will be our 2 cell. So what you do is you break this into individual components. So we have our 5 vertices, we have our 5 edges, and we have our 1 face. So those are denoted by this here. So and this denotes the dimension of the cell. And what you do is you define this K-chain, where K is equal to the dimension. Editing Gabriel here, and I realized that I said K-chains for the entire video. K-chains are different from K-cochains. In the paper, the map they use is a K-cochain. And every time I say K-chain, I actually mean K-cochain. So anyone who knows topology or homology, I'm sorry. I'm going to be saying K-chain the entire time. So the K-chain is basically to simplify it down really far, it's basically the components, while the K-cochain is this map that I mentioned in the video. So the map between, so if this is my cellular complex here with only 0 cells and 0 components and 1 components, the K-chain itself would basically be a sum, if we're talking about this more generally. But to simplify it, I'll just say it's like this collection of vertices here. So the collection here would be these 3 vertices here. And that would be our 0 chain for where K is equal to 0. So K-chain of vertices is a 0 chain. And the K-cochain is what I mentioned in the video. It's the map on the vertices. A one-chain would be the kind of collection, again, not using rigorous math terms, just using very broad terms here that are not super specific, because I don't know the theory super well with K-chains, and nor is this a video on K-chains. Others can explain it much better, but it's basically the edges here. So the K-chain itself is the structure, while the K-cochain is a map on that structure. So just want to fix that. I'm going to be saying K-chain the whole time. I actually mean K-cochain. This would be a K-chain where K is equal to 1, and this would be a K-chain where K is equal to 2. And we can map this. We can have a one-to-one mapping between the vertices, or between the components of the cells. So we can have a mapping between the cells and the corresponding vectors to the cells. So over here we have these vectors here that correspond to those cells, and these vectors are going to be our features for every single part of for every single vertex, edge, and face. So that's how we're constructing our space. And this is similar to what you would normally see in a graph neural network. You would have vertices, where the vertices would have these features, but instead we're having features on the edges in the face as well. And you can just define this as a matrix where that looks like this, where this for each K-chain. And remember, a K-chain corresponds to the kth dimension. So we would have 3 K-chains in this case, one for the 0th dimension, one for the first, and one for the second dimension. And you define that as a matrix where this, where the rows are your cells of rank K. So that would be like an index saying, oh, this is my first vertex, and this is my second vertex. And then this would be the data. Your rows would be, your columns would be your data. So you would have a vector here. So that's how you would kind of represent the space and its features. Now, I guess they define it really well in here because it's not super abstract. This is literally just a map from your manifold or from your cellular complex to every part of it to a real space, just RD, where you're just defining these features on your cell. On your cellular complex. But they actually, this is generally a map from a topological space that can be any space to any abelian space. And that's what a K-chain is. But I just want to put that out there in case there's somebody watching this who's like, hey, that's not a map from a cellular complex to a real space. It's actually a map from a topological space to an abelian space. But that's why, if you look in the literature, the K-chains are defined really strangely. So one extra thing we had to define before we get to modeling this in a transformer. Well, there's 2 things, but one thing that I want to define first is, how do you kind of define neighbors, and how do you define a structured matrix describing this space? So what you can do is you can define this boundary matrix. So here are incidence relations. In this case, it's going to be boundaries. So I'm not going to go any further to incidence relations. I'm just going to talk about the boundaries for our K-chain or for our cell. So that's, I'm just going to talk about those because we're going to need those later. So basically, we can define this boundary operator here as basically boundaries from, say, one cell to a 0 cell. So that would be the boundary between these vertices and the edges. And we can define a boundary between those. So intuitively, we can look here and we can say we have this face. And this face has a boundary, and the boundary on this face is made up of edges. So intuitively, we can see that. This goes for any cell. So if you have a 3-dimensional cell, it also goes for that, where the boundary is 1 dimension lower, But if you take the boundary of the boundary, it doesn't exist. But basically, what we're saying is we have this boundary, and this boundary is going to be one-dimensional lower than the cell we're working on. So in our case, since we're only working with 0 cells, 1 cells, and 2 cells, the 2 cells are going to have a boundary of these edges, and the edges, which are our 1 cells, are going to have boundaries of vertices. And this will be useful for message passing. And this is common for this. I've seen this. This is common for literature on topological message passing on simplices. So basically kind of a less version of cellular complexes and cellular complexes. So the way we can do that is, say, over here. Well, I'll go ahead and go through what they say first. So basically, we want to define this relationship between cells of consecutive rank, and they're encoded into these matrices. So the first matrix, B1, has ij entries where the value is -1. If the jth edge, ej, starts at the ith vertex, vi, and 1 if ej starts at vi and 0 otherwise, or ends at vi. So the way you can visualize that is over here. If this is our space right here, I'm only going to draw out B1, but you can see this for B2, where B1 is the relationship between vertices and edges, and B2 is the relationship between edges and faces. So here we're saying our vertices are going to be are going to be denoted by I, and our edges are going to be denoted by J. So that's what they were talking about over here. And we have our space over here, which is just going to be edges, and I just want to make it really simple to show how this works. So we have 2 edges here. We have an edge A, which is between A and B, and we have an edge B, which is between B and C, and we have our 3 vertices here, which are A, B, and C. Lowercase for the vertices, uppercase for the edges, just to denote them. Now our matrix here is going to be a 3x2 matrix, and what we have is we have a -1 if it starts there. So for edge A, if we look at edge A, we're going to give a value of -1 since edge A starts at vertex A, and a value of 1 because edge A ends at B, and then a value of 0 because it doesn't have any relationship to C. So if we have a larger matrix and we have a lot more vertices and edges, every edge is just going to have 2 parts to it because it's connecting vertices, while a face can have a lot more because a face has more than, it can have 3 or more edges. So, yeah, this is a really sparse matrix just for vertices. Now for B, if we look at B, it's the same idea. B starts at vertex B, so we give it a value of -1, and it ends at C, so we give a value of 1. So this is our boundary matrix here. Now we can denote this with B1 because this represents the boundaries of the 1 cell. So boundaries of the 1 cell, which are vertices, or which are edges. So our 1 cells are edges, and the boundary of vertices. Now B2 are the boundary of edges, or are the boundary of faces. This is wrong. This would be faces, and this would be edges. So this is just the extension of this to 1 dimension higher, and it's the exact same idea as this. They mention over here. The entries of the second matrix B2 are the numbers between faces and edges, where the number of a face with an edge is the sign plus or minus e if it belongs to a closed path of the edges on the face, and 0 otherwise. So basically, is it on some closed path around the face? And if it is, then it's going to have a value of plus or minus e, depending on the direction of e. So you can define a direction on e, or you can not, and that gives you your value here. So these are the matrices defining your boundaries. And of course, this goes higher order, but we're not worrying about that. Now, one more thing is we can define these non-signed versions denoted ik instead of B1, it would be I1, which just takes the absolute value of this And that's what we're going to use. It's just the non-signed version. So yeah, we now have all our information to talk about the transformer, and it does what you would expect. Basically, we're going to pass all the features through, and yeah, we're going to work on that. We also need these positional encodings, and the positional encodings are the thing that gets really, really into the topology, and that's the part that I'm like, I do not know what the heck it's talking about. But let's talk about the transformer. So the transformer has two parts to it. They have this, if we look here, they have this pairwise, not pairwise, pairwise cellular attention, which is basically saying we can pass information between these K-chains. And remember, a K-chain is, so a K-chain is a space RD kind of attached to each cellular complex, where K is denoting the dimension, and the data that's kind of assigned to it is in some real dimension that we define. These are just vectors, and the vectors are assigned to each part of the K-chain. But you can denote these differently from each other. So this is going to be our 0th K-chain here, which is just with vertex information, and this is going to be our first K-chain, which is just going to be edge information. And this can have different dimension. These can have different dimensions. It's easy to assume that they don't have different dimensions, but they can have different dimensions. And the first approach is going to deal with the different dimensions, and the second one is not. But it's easy to just assume that they do. I'm going to talk about both kind of at the same time. I guess it would be a lot easier to talk about the general cellular attention case, but from this diagram here. So let me erase all this because it's a mess. So we have these K-chains, and we basically want to define a map from K-chain to K-chain. So let's say we only deal with K-chain 0, so where K is equal to 0. So what that would mean is if we do attention on the K-chain of 0, then we're only doing attention on the cells or not the cells, but on the vertices between each other. And this would be like normal attention, where you're only doing attention on these vertices. So in the example over here, we have 5 vertices. You would basically have 5 features, and it would be normal attention, where you have your 5x5 matrix as your as your attention matrix, and this would define a routing between your vertices. So this is basically normal attention if we say K is equal to 0. So let's talk about it in that sense. So let's say X has a value where K is equal to 0. So this X here is just our matrix, our feature matrix for vertices. So in this case, we just project it via this Q matrix. So normal Q projection, where you're putting it in some decay projection, or some decay dimension. So this is just changing the dimension for the queries. This right here is changing the dimension for the keys, and this right here is changing the dimension for the values. So normal Q, K, and V projections here. Now, if we just look at that, then if this was Q and this was K and this was V, then all we have is QK transpose, the softmax of QK transpose, which is this here, which you will recall is just the normal attention matrix, times this here, which we'll get to in a second, multiplied by V here. So this is just normal attention between our vertices, except we have this. So first, so just think of this as the mask for now. So if this was a mask here, usually you add the mask before softmax, but we'll get to kind of why it's being multiplied in a second. To generalize this, this is going to be attention between different K-chains. So you can obviously have self-attention. So if this is K is equal to 0, then, and this is K is equal to 0, or rather, let's look at the map here. So we have these two parts here. This can be self-attention if we say this is a map where the queries and the keys the queries and the keys are both dealing with the 0th dimension. Note that the k's are different here. So we can also define this as a cross attention where the edges can attend to the vertices. So if we define this here as our features on our vertices like we did before, where k is equal to 0, and we define this as our features on our edges, then we can define this cross attention here. And cross attention works like you would expect normal cross attention. It just is denoted weirdly and differently here. So that's what we can do. We can do self-attention on one K-chain, or we can do cross-attention between K-chains. And then we have this here, so our mask. So like we're not trying to do word prediction here. So what the heck is this mask going to be? We can have bidirectional attention. So this mask is going to be a mask telling you, kind of restraining the attention to boundaries and basically applying some structure to your attention so that it can't just go everywhere. So this mask here is basically going to come from our boundary relations or the incident matrices above. So basically, if we look here, this will be our boundary. This will be our mask here, but this is kind of a mask for later. But let's say we do self-attention on the vertices, then this will give you this mask here, and this mask here is basically going to be our upper adjacencies, which I'll talk about in a second. And then if we do self-attention on the edges and the faces, this will be lower adjacencies. So they basically say that they define this mask, and this mask is going to have structure. And what structure is it going to have? Well, if we're doing self-attention, then the structure we're going to have is, if we're dealing with self-attention on the vertices, we're going to have upper adjacencies as our mask. If we're dealing with k is equal to 1, 2, or higher, we're going to have lower adjacencies. So this is a special case here. And if we're doing cross attention between, say, edges and vertices, so edges and vertices here, then we're going to have this instance matrix here, which defines our boundaries. And basically, this will give you matrices for these K-chains that are one-off. So if you have this attention, if you have cross attention between your vertices and your faces, this should be 0, because on a face, there is no boundary made of vertices. There are vertices on the face, but that's not a boundary. Those are just on the face. The boundary is just one dimension off. So I'll get to why I constructed this later. That goes into the second attention method. So let's talk about these upper and lower adjacencies. I just defined them up here. Basically, an upper adjacency is two matrices, or two vertices, and I'm just going to talk about the vertices and edges, but this can obviously go into higher dimensions. Basically, an upper adjacency is two vertices are upper adjacent if they share the same edge. So intuitively, what that would look like is if I have this here, and I'll denote this as A, B, and C, these two vertices here are upper adjacent by edge, by this edge here. So because they're both attached to that edge, but A and C would not be upper adjacent because they're not attached to an edge. And this goes higher dimension. So two edges are upper adjacent if they share the same face. So that would be this mask. That would be this mask here. So basically, we're saying that the vertices can only attend to each other if they share a common edge. Now let's go to lower adjacency. I don't know why I have any there, but lower adjacencies are kind of the opposite. Two edges are lower adjacent if they share the same vertex. So this is going down. This is looking downward. So if we have this here, and let's say we denote this as A, B, and C, and this is A and B. So the edges are, like I denoted before, the uppercase. Basically, we have edge A is upper adjacent to edge, or is lower adjacent to edge B because they share edge B. Maybe I'll add another one, C. So edge C here is lower adjacent to edge A because of vertex A. So they share a common vertex. But edge C is not lower adjacent to edge B because they do not share a common vertex. So basically, for self-attention on edges and faces, you have these, you do attention between edges if they share a common vertex, and you do attention between faces if they share a common edge. So that's the idea here. Now, the boundary matrices here basically say we're going to do attention on the boundaries. So cross-attention between edges and vertices, that would basically, and you flip it depending on if you're doing attention from vertices to edges or attention from edges to vertices. But no matter what cross-attention you're doing, information flows between dimensions of order 1 greater. So edges can attend to vertices, vertices can attend to edges, but vertices cannot attend to faces because there is no boundary. So this is the idea for pairwise cellular attention. Basically, it's normal attention, except you're doing it on the cell complexes, and the cell complexes can attend to each other based off the relations described above here. Now, we can define this general cellular attention by just saying, well, what if we throw everything together? So basically what I show up here. What if we just attach everything together and have attention over everything? So initially we had attention. So like if this represents all our features, so we have 3 edges or 3 vertices, 3 edges, and 3 faces. Is this an impossible construction? Yes. You cannot have 3 faces, 3 edges, and 3 vertices. You should try to construct that. Yeah, it's impossible. But for the sake of me not having to draw a ton of things, I'm making it 3 vertices, 3 edges, and 3 faces. So what our attention matrix would look like for the first attention method is it would basically be attention on each of these blocks here. So it would be either a self-attention or a cross-attention. And the softmax would be applied to each of these matrices here that you're attending to. So you basically attend to every part individually. Now this general attention is saying, well, what if you just concatenate all these together and do attention on this big matrix here, where this is our mask, obviously. So you would have your QK transpose here. You would apply softmax over this, where this attention matrix here is the attention from every vertex, every edge, and every face to every vertex, every edge, and every face. You would apply softmax, and then you mask it with this matrix here, where this matrix is what I described before, with the relationships on the boundary and the relationships on itself, except you're just doing it all at once. So you either do it all at once and you do this global attention, or you do it individually. And these have different properties because one is a softmax on each part, it's a local attention, and the other is just global attention that you're doing with the same mask. So that's the idea between these two. And this is denoted by this mess here, but yeah. Now, if we look here, just so I can show a picture of these two. I mean, they look the same pretty much. But just to show these relationships here, if these are vertices, these are edges, and these are faces, like I mentioned the relationships. So I is going to be our boundary. So we can have I be between edges and vertices, as you see here. So this is kind of the cross attention. We're saying that the vertices can attend to the edges can attend to the vertices. But notice there is no relationship here between the vertices and the faces because there is no boundary. And then you have the boundary of the faces, which are the edges here. And then you have self-attention, where this is your upper adjacency, and these are your lower adjacencies for higher dimensions. So that's the idea. Now, one thing I need to mention is the positional encoding. So intuitively, for positional encoding in text, you have a sequence. And the sequence tells you, you want to know what position each word is in, because attention does not work with sequences. It natively works with unordered sets. So you need to add positional encoding so that it works with sequences. Now, the sequence information here is kind of unintuitive, But basically what you want to do is you want to encode kind of where something is in the graph. Right now, we don't have anything encoding any structure information. We basically took all the vertices, we took all the edges, and we took all the faces, and we just converted them all to features. If I go up here, this is what we see over here, but the transformer sees this here, and it just sees a concatenation of all these. And it says, oh, these are my features for my vertices, these are my features for my edges, and maybe these are my features for my faces. So maybe it knows, it'll know the difference between faces and vertices, but it has no idea what the connections, well, it has some idea what the connections are because we're defining that through the boundary maps, but we still want to define these positional encodings telling it information about these parts. Because like I mentioned, without that, it would be kind of clueless and kind of lost. It can't get everything from the boundary maps we define with it. So they define these three methods, and I don't really know exactly how they're working. So if anyone has some good resources or knows exactly what they're doing with these methods, that would be awesome. You could throw some information or throw some information in comments or something. But there's these three positional encodings they do. One are these barycentric subdivision positional encodings. They use this Hodge-Laplacian, and they take the eigenvectors, and from what I know, the eigenvectors of the Laplacian of the graph basically tell you, like, it gives you this structure, like the number of connected components and the number of kind of choke points depending on the eigenvalue you're looking at. So that's what I know for this one here. So this is kind of more like a global positional encoding. This one here, it's a random walk. We know random walks, but basically they take this cell here. So this is some cell. They turn it into these barycentric subdivisions. So basically defining these vertices. So instead of having your face here, you're going to have this structured vertex here. And the reason you do that is so you can do your random walk on it. And then they define this one skeleton, and the one skeleton is going to be composed of all the edges and the vertices. And then you can do a random walk like normal on this graph. And doing a random walk will give you a positional encoding for each of these, basically encoding where this is in the graph, kind of in a local area, because you're doing a random walk. So random walks are always nice. They're always a nice way to define position in a graph. And then there's Slepians. I don't know if I'd pronounced that right, and I do not know what these are. I'm not going to pretend like I do. But this is another way they do positional encoding. I like this way the best, because this way makes a lot of sense to me. But all three are kind of similar in how they perform. It depends on the task. So the problem with that's the method. Basically, you're converting this. You're converting these cells to features via these K-chains, and you just do attention on them in different ways. And you need to add these crazy positional encodings to do that. So that's the method, and they have a few datasets they work with. So there's these graph datasets. They use GCB, Zinc, and OB or OGBG. They're like these normal graph datasets, like you've probably seen Zinc before if you've looked at some graph neural network literature. But they define these three, but the problem is they use these three. And the problem with them is they only have these pairwise relations. So what they do is they do the lifting procedure I described before, where basically if you have this cycle or this boundary, you fill it with a face because it only has vertices and edges. And then they just go up to 2 cells, so they only deal with faces and they don't go higher than that. Now if we look here at how it performs decently well across the board. It doesn't do like the best out of everything. It does really well on GCB, but for the other 2 benchmarks, it doesn't do super crazy. But I mean, it's cool that it can do this well because it was meant to work on cells. It wasn't, and cells are kind of in a level higher than graph neural networks. But I think it would be, I think it's a cool direction, even though it only it doesn't outperform everything like crazy. And there also needs to be more benchmarks to see if this works better. But yeah, these are all the benchmarks they kind of have. So you don't know how well it works because there's not that many graph neural network benchmarks. Here we have kind of how it works with different positional encodings here, and on different tasks and with different structures here. They have global attention, dense and sparse attention. And the difference between dense and sparse attention is the dense and sparse one is they basically put a function around the mask that I defined earlier, and the function basically allows it to attend everywhere just with the information from the boundary. So if you throw a function on that, so like a feed-forward layer, it can attend everywhere because the feed-forward layer is going to output components that are not 1 or 0. So that's the dense approach versus the sparse approach. One can only attend on the boundary, one can attend everywhere, but it utilizes the boundary information. So it does, in general, it's kind of like all over the place depending on the, like global attention or general attention seems to do the best, but all of them seem to be pretty similar in terms of how well they do. And the positional encodings also seem to be similar in that sense. So, and then they also have these general versus pairwise attention. So normal pairwise attention is normal attention, and then general is the first attention mechanism they defined, and then general is the second attention mechanism they defined. Sorry, not normal attention. So general attention using common query key projections for all cells at the same time is more suitable for problems where features in all ranks are homogeneous, i.e. all the same nature. And pairwise attention that uses more specific query key projections for pairwise ranks is more suitable for problems where features are heterogeneous because it allows for each rank to attend to specific properties of each rank in an isolated way. So more specific versus more global, rather. So one works for homogeneous cases and one works for heterogeneous, but these are what they saw in only a few data sets. I don't know how accurate that is. But I think this is a cool approach to working with cellular complexes.